In the last video of this course, so sad, we're going to talk about some applications of these LTI systems. And namely, we're going to look at applications that we can use to differ between all the frequencies that we have obtained from our function. So we have y omega, which is great. So what can we do with that? Well, we have filters. Filters are one of the things that we can use. For example, we have a low pass filter. And a low pass in itself can be seen, of course, as a system where it is 1 only if the frequency is below a certain cutoff frequency and 0 otherwise. And this cutoff frequency you choose yourself. But what we get is we have, of course, these axes here, and this function just looks like this. It looks like actually two step functions subtracted from each other. And all the frequencies that are in this area, not just this area, but actually in this range, will be let through and the other ones will be deleted. In the end, we will look at an example of such filters. After the low pass, we of course also have a high pass. And the names are actually very self-explanatory. This is a 1 if our frequency is higher than our specific cutoff frequency, and it is 0 otherwise. So before I'm going to draw this, try to draw it in your head how it would look like. This was a low pass filter because the 0th frequency is in the middle. So what would a high pass filter look like? Well, exactly the opposite. It will let through all the high frequencies. All frequencies that are in the range where the surface is bigger than 0. Now, there was a low pass, there was a high pass, then we're going to a band pass filter. And a band pass filter is defined as a 1 if the frequency is between two chosen frequencies and 0 otherwise. And how does this one look? Try to imagine it for yourself. But what it actually does is it chooses a band to pass. So there are two spots. And all the frequencies where the surface is not 0. Again, this is the range of frequencies that we are letting through. Well, since we have a band pass filter, we also have a band stop filter. And a band stop filter is just the same as a band pass, only again turned around. So it is a 0 if our frequency is in between these values, and it is a 1 otherwise. So once again, we will draw it quickly, because if it is the exact opposite, we already know what it's going to look like. Somewhat like this. Everywhere where the surface is not 0, in that range of frequencies we will let through. Furthermore, if you look at a band pass filter, then the bandwidth of all the frequency that is let through is calculated with omega 2 minus omega 1. They know what the bandwidth is. And these are all filters, and all these filters can be interpreted as LTI systems, and you can even cascade multiple filters into one. So let's take a look at applying these filters. Recall that at a very earlier video we had the following function. 4 plus 2 times the cosine of 120 pi t plus pi over 6 plus 6 cosine of 220 pi t minus pi over 3. And with this, we calculated the frequencies and the amplitude that came with it in a stem plot. These frequencies we can draw again. So at a frequency of 0, we actually had a length of 4. At a frequency of minus 60 and 60, and at frequencies of minus 110 and 110, 110, 60 and minus 60, we had the following amplitudes as well: 3e I pi divided by 3 and 3e minus I pi divided by 3. For the other ones, we had e to the power of minus I pi divided by 6. And for this one, we had e to the power of I pi divided by 6. If you're wondering how do we get to these frequency values, I advise you to look at one of the earlier videos where we look at the Fourier analysis and synthesis of writing a function from time domain to the frequency domain. Now let's say we are letting loose a low pass filter on this. And the low pass filter we're going to create at an omega of 200 pi. Any frequency above this is cut off. So if we are going to translate that to the frequencies we have here, 200 pi translates to a frequency of 100. So anything above here, all the way to the right here, somewhere around here, this should be at 100 and this should be at minus 100. Every frequency that is in here is taken into account. So actually only these frequencies, this one, the 0th one, the amplitude, and this one are considered. And why are these low pass filters, for example, so necessary or very nice? Well, for example, if we are listening to voices or to sound or to music and we want to record that, we do not need any frequency that is higher than 22.1 kHz, because anything higher than that we humans cannot hear. So to record something, we're actually passing it through a continuous to discrete system that also has a low pass filter that just removes any unnecessary frequencies from our spectrum. And all the other filters that we have seen here, the low next to low pass, we also have the high pass, the band pass, bandwidth, and band stop. These all have their own niche little use and can be used in many different applications. And how these are usually denoted are with our HP or H low pass. The high pass is with H, so this is of omega. And of course, high pass is HP. For band pass, we're looking at HBP. For the band stop, we're looking at an H of BS. So these are the functions usually associated with these filters, and they are just used usually after you have calculated your Y omega, but you can also interpret them as systems themselves, where they apply a certain function or a translation to a function that's put into, because you're just removing the filters or removing the frequencies that are too high or too low or anything. And this concludes the last video of applied mathematics. If you have any questions or feedback, please mail them to the secretary of Cognac so they can mail them to me. And good luck with your exam.